Hi, my name is Deborah Hanus, and today I'm going to talk about some of the challenges in making machine learning for healthcare work. Just to tell you about my background, I did my undergraduate and my master's at MIT in computer science, and I did all of my undergraduate research in developing computational models of how humans perceive things. I spent a year in Cambodia working as a Fulbright scholar, and then I spent some time in San Francisco where working as a software engineer. And then I decided to quit life and become a PhD student, where I've been working on a lot of really interesting projects at the intersection of machine learning and healthcare. And I feel like I know machine learning fairly well. I've definitely come up with against a lot of challenges when trying to combine machine learning and healthcare, just because it is a very unique intersection. And so today we'll talk about some of those challenges and how to manage some of those challenges. And then we'll go more in depth into one of the projects that I've worked on early in my PhD. So first, why is machine learning for healthcare different? One is, error management is very important. It's important that you present your results clearly if you're going to be working with someone in the medical profession. Domain knowledge is also very important. And then you can mitigate some of these issues using an effective data collection and representation. And then finally, we'll talk about how to deal with incomplete data, because when working with healthcare data, it's very rarely do you have all of the information. So we'll spend some time talking about that. So in general, computers can recognize scenes and objects very well. This is a very cool demo that comes from Antonio Torralba's group at MIT. If you go to places.csale.mit.edu, you can upload an image and it'll tell you what is in the image. So in this case, you have a picture of a swimming pool. It tells you this is outdoors. It's a swimming pool. It's probably a sandbar. So that's very effective. We also have this one where we see a bunch of people standing in line, and it tells us that this is an indoor environment. It's probably an airport terminal, and I would totally believe that. It looks kind of like an airport terminal to me. So I'd say this is doing about as well as I would do on these pictures. So that's great. It seems like computer vision is great at doing this identification, except when it's not. So like in this case, we have a goose and it's identified this wave as a car. And in general, this isn't a big problem. I mean, almost all learning involves some type of errors. But in the case of working with healthcare, having any sort of error can be a huge deal. If you accidentally misidentify someone has a cancer tumor or something like that in an image, then you're probably going to cause them a lot of emotional trauma, their family a lot of emotional trauma. You'll cause the hospital and their insurance company a lot of money in order to treat the cancer, which might not be there. So it's really important that you build things that really work well with the data that you have and have a very good accuracy. Okay. So you need to manage errors a little bit differently when you're working with healthcare. And another issue is that you need to be very clear about how you present your results. So most doctors don't know a lot about machine learning. They've spent many years in medical school, and it's just too much time to spend 10 years in medical school, another 10 years in a machine learning PhD. And they have this issue, which is if they do what has always been done, no one will think any worse of them for it. Whereas if they try something new, like a new machine learning algorithm to assist them in doing their job, they take on some liability for doing that. So in order to take on this extra responsibility of using the machine learning algorithm, they need to be convinced that the machine algorithm will work, and they have to have some sort of trust for the algorithm. So in this case, I'd say it's especially important when you're working with medical data and building things for healthcare, that you make sure that your results are interpretable and they can be not only be used by humans, but a human who doesn't know machine learning can still feel like they trust that it's doing what it should. A nice real life example of this that a lot of people are familiar with is something like autocomplete on your phone. So in this case, you might say the cars, the kids, the cans, and you can sort of see which of the computer will pick which of those it thinks is most probable. And if you think it has picked the wrong one, then you can go and you can select one of the others. So it sort of makes you, it does a lot of the work for you by picking out some of the words that you could use, but it leaves the final decision to you so that you can trust what it's doing. So we've talked about managing errors, making sure that the results are clear. And now we'll spend some time talking about another challenge, which is just understanding what's going on in the data. So a good example of this is if you're working with patient vitals. Are some common sense of patient vital signs that a lot of people use. And these include blood pressure, heart rate, blood oxygenation level. And so if any of you have been to the hospital, you might have seen a device like this that collects your blood oxygenation. You just put your finger into it, and it tells you how much oxygen is in your blood. And it's common when people are looking at this data set, they'll notice that there are a lot of 62s. You might be looking at a healthy patient with 100% blood oxygenation, and then suddenly it drops down to 62. It might be an unhealthy patient, and you're like, wow, well, like, what's going on with this? Like, their blood pressure's fine, their heart rate's fine. Why is their blood oxygenation level so low? But then if you learn more about how the data is collected, you'll know that it's kind of a lot of trouble to turn these machines on and off. So usually the care providers will just leave them on the entire time. They'll collect the patient's information, and then when the patient leaves, they'll just drop it down on the white sheet, and it turns out that a white hospital sheet has 62% oxygenation. So if you don't know this from working with these oximeters all the time, this can be very, very confusing. So it's important that you get a good collaborator and you understand how your data is being collected, since you're usually not able to collect it yourself. Another great example of this is working with electronic health records. You might do something like have a goal of find how long the patient has had diabetes. So you might think one of the most obvious ways that you could do this is look at the diagnosis code. We know what day today is. We know the date they were diagnosed. We'll just subtract these, and then we know how long a patient has had diabetes. But if you're looking at, if you look at the US insurance system, often you need a diagnosis code in order to have a test covered. So if I'm going to go in and get tested for diabetes, first I need to be diagnosed as having diabetes in order to have the insurance cover my test. If I get tested without that diagnosis code, then the insurance will treat it like this is a test irrelevant for you. Why would you get treated for that? And they wouldn't be willing to cover it. So you have a lot of people who have diabetes diagnosis codes who might not actually have diabetes. They might have gotten a negative result on that test. So another way we could do this is we could try to turn this into some sort of supervised learning problem, where we look at patients that we know that we're pretty sure have diabetes, and we look at what factors they have, what features are in their medical record, and we look at other patients that we think don't have diabetes. But the problem is we think that they don't have diabetes. Some of these patients might have, they might be pre-diabetic. They might have a history of diabetes, so that some of the factors in their blood are similar to someone who does have diabetes. So this is something that we need to be thinking about as we're designing our solution. Another way that we can manage this is we could maybe create some sort of rule where, like, if a patient has greater than 6 treatments for diabetes in the first, in 3 months' time, then we'll say that the start of that time period is when they had diabetes and when the onset was. So we spent some time talking about some issues where it's important that you have some domain knowledge and some ways that this might come up. So it would be reasonable to wonder, how can you get this domain knowledge? One way is you could go become a doctor, nurse, or technician and get really familiar with the data that the collection process for this data in a certain hospital. You can probably, sometimes you can shadow a doctor, nurse, or technician for a while to learn a bit about it yourself, if you have a good collaborator who's open to that. But probably the easiest way is to just find a great collaborator in the hospital system who doesn't have to understand machine learning. They just have to understand how they collect the data, how they use the data, and ask a lot of questions. Start out by asking a lot of questions. And if you find some results, go back to them, say, do these results make sense? If you find something surprising, talk to them about it. And just make sure that you have open communication lines throughout the whole process. And then one way that you can manage a lot of this is with a good process for data collection and representation. And so one way that you can get this data is, as I mentioned, with these collaborations with hospitals. Notably, there can be a lot of administrative overhead in collaborating with hospitals, even if you have a doctor who you're working with, who really wants to work with you and you really want to work with them. Often it can still take several months to years to actually get access to the data, and even longer to figure out how to work with the hospital servers to make sure that you understand the data. Another way is to find some of this data which is publicly available, such as you can find some data on health forums. So if someone has a certain disease, there is often some forum for people who have this disease to go and talk about what's working for them, what isn't. And Finale Doshi-Velez is doing a lot of interesting work in this area. Another is social media, and Mark Dresdy at Johns Hopkins is doing a lot of cool things with this. Apparently, you can get a lot of interesting information about medical information from Twitter and other social media like that, because sometimes people post about these things. Sometimes you might also be able to find other factors that are correlated. So there's a lot of interesting data that you can get everywhere from this, although the most direct and effective data is probably going to be with these collaborations with hospitals. So now, if we have the data, there are still a lot of things that we need to think of, one of which is this data is sort of inherently biased. If we're getting our data from the hospital probably solves or probably works with a certain metropolitan area and gets a lot of people from that area who come in as patients. And within a certain area, people might be more predisposed to certain diseases. There might be more people who are exposed to similar things. And then you also just have the problem that no matter where your hospital is, people usually only come to the hospital when they're sick. So sometimes you can have difficulty finding healthy patients to compare things to. And there are a lot of other issues that can come up there. So we've talked about a lot of the things that we need to think about when working with healthcare data. And now let's talk about dealing with incomplete data. So there are several types of missing data. One is data can be missing at random. Data can be missing not at random, or data can be missing completely not at random. And the first time I saw these, they all sounded exactly the same to me. So we'll go into some examples next. So data can be missing at random, and this means that the events that lead to the missing data occurred at random, but the probability of the data being missing is dependent on other variables. So an example of this might be the likelihood of a certain medical test being performed might be dependent on the patient's health insurance. So years ago, they selected some insurance from an insurance marketplace, not knowing that they would get sick, and then you prescribe this test, then the doctor prescribed this test, and then if their insurance covers it, they'll get the test, and if their insurance doesn't cover it, they won't get the test. So this would mean that the data is missing at random. The data can also be missing not at random, and that means that the probability of the variable being missing depends on itself. So an example of this might be a patient with a low risk of HIV might get tested for HIV less often. Makes sense. The data can also be missing completely at random. And this means that the patient does not get the test, so the data is missing, but has nothing to do with anything else. As you can imagine, this doesn't happen very often because often things are very interrelated. But in this case, in this very unusual case, you can ignore missing data without bias. So now we're going to discuss a case study and a project that I worked on in the first year of my PhD, using reinforcement learning to predict effective HIV treatments, particularly in the presence of missing data. So to start off with, I'll give you some background so that you can understand the project. So many of you probably know that HIV is a potential precursor to AIDS. Patients with AIDS have an increased susceptibility to disease. So it's ideal to treat this before it becomes AIDS. And a common way of treating this is structured treatment interruption. So you get some combination of drugs that cycle on and off. And the drugs are strong, they hit everything in your immune system, the good and the bad. So it's during the off periods that your immune system gets the boost that it needs to start becoming a bit healthier. And then you can model when you should cycle these drugs on and off using reinforcement learning. So reinforcement learning is just a formulation of a problem where you have an agent that you're controlling, and you have a state space which defines which items of the environment you're looking at, a set of actions, which is how the agent interacts with the environment, and then the goal is usually to maximize some reward function. In this case, we're saying the states are these health indicators in the blood. So the patient goes in, gets a blood test, and you can count certain factors in the blood. And the actions are the drugs that can be applied. The reward measures the effect of those actions. And the goal is to maximize this reward function so that we get to healthy patient as soon as possible. So these states are these personal health indicators. The patient goes in, gets a blood test, can count in a certain volume of blood the number of healthy CD4 plus T lymphocytes, the number of healthy macrophages. And some of these things are good and some of these things are bad. The actions are the potential drugs. So some common drugs used for treating this are a protease inhibitor and a reverse transcriptase inhibitor. So you could use those separately, you could use both, or you could use none. And the reward is this linear combination of states and constants. So if you have more of these indications of an unhealthy patient, like unhealthy macrophages, free virus particles, that will decrease the reward. And if you have more healthy indicators like healthy macrophages, that will increase the reward. Our goal is to maximize this reward function. So this is so the simulator makes a couple of assumptions. One of the assumptions is that the patient goes to the hospital for full treatment and testing once every 5 days. And so if this happens, you can see this actually works pretty well. The blue line indicates a random policy. So this would mean that we don't look at anything about the state and we just randomly select protease inhibitor, reverse transcriptase inhibitor, nothing. And you can see that this does quite a bit better than random. So now you might be thinking, problem solved, can move on from here. But this is very unusual. And it can be very difficult for someone to actually make it to their hospital once every 5 days. You can imagine if you live in a city without good public transportation, or you don't live close to a hospital, or you or you work an hourly job, you might not be able to get every 5th day off of work. So we wanted to relax some of the assumptions of the simulator and say, what if instead we say that the patient, rather than having the patient come in once every 5 days, we say that the patient comes into the hospital randomly. So one way we can do this is we say the patient comes in on Monday, the patient comes in 2 weeks from now, the patient comes in 3 weeks from now, 2 weeks from now, they just come in whenever. Another is we look at this sort of paired data where we say like, I'm a patient, I come in Monday, I come in Friday, but then it doesn't matter the next time I come in 2 weeks from now, 3 weeks from now. So we looked at these two different types of missing data. And then we looked at some ways that we could deal with this. So just one way that, some ways that you deal with missing data are first, you could ignore it, but this only works if you assume your data is MCAR, which, given that this is time series data, it seems very likely that it is not. Another way that you can deal with this is you can interpolate missing values. So you come up with some model for how you think the data is going to change. So one case of this is like linear interpolation. If you know the two blue points, you can guess that if you're doing linear interpolation, the red point is where there is a reasonable guess at what the data at that point might be. So we did try interpolating some of the data. Another way you could do this is with imputation. So you can use sampling. So in this case, we use sampling from the posterior and then Bayesian linear regression to impute the data. So in this case, we said there is going to be, we know what the data is at the black X's. We don't know what they are at the gray X's, so we're going to guess by saying that there's some Gaussian distribution which increases in variance, and then we'll sample from that. And assuming a linear relationship, and then by sampling that, we'll get, we use a modified expectation maximization to settle in on some reasonable value. Another is develop a more complex model, like why is the data missing? Are there any patterns using some Gaussian processes? And this is not our data, but it gives you an idea of what that sort of process can look like. And so then these were the results that we got. So you can see and notably this is just one data point. You can see that with the complete data set, it still performs quite well. The sparse data performs even better, and then the paired data is a little bit less good. And we did this work at Harvard, working with Finale and Taylor, and it's funded by the National Science Foundation. And that's everything right now. Okay, so I was looking at my slides. So just now I'm seeing everyone's questions. So I guess if you could give me some context, that would be helpful. The first question is, what is the speaker's full name? It is Deborah Hanus, yes. What about his lab results? Gilbert says, if I have a model that recognizes lung cancer in images and its performance is superhuman, let's say it says a person has cancer, but it's not visible for the human eye, but in 3 months it might be. How do you deal with such a case? Do you start treatment or do you wait for it to be visible too late? That is a good philosophical question. I think that you would need a lot of, you would need to definitely have a doctor very on board with that. And I think that if it could actually, if you could actually reliably have results in advance that everyone knows are better than what a human can do, then it's possible that you could get that early, you could take care of it earlier. But I think a lot of that is going to rely on how good your cooperation is with the doctors. Another question is, how are developers increasing their knowledge on how to work with medical data? From Charlie. And I mean, these are some of the ways I discussed here, some of the things that I've learned. I'm sure that other people might have some good answers to Charlie's questions. You should feel free to chime in. Parsa, it is difficult to use a neuro-fuzzy approach to deal with missing data issue. Use a neuro. I'm not sure I understand what you mean by neuro-fuzzy approach, but if you have more questions, we can talk more about it offline. Let's see, COVID says, can I name a few cases where ML has helped in the medical sciences? Yes, there are many cases. I guess, although one thing that I would note is I think that right now a good approach to precision medicine is to look at ways that we can assist doctors in doing their jobs better. I think some people think that the goal should be replacing doctors, and I think we're not going to get there in this generation. So one thing that some projects that I think I've been excited about are actually relatively simple. There is an example of this is commonly doctors write incorrect prescriptions, just like they'll put the decimal point in the wrong place. So you can have something that's very simple that just has a lookup table of what common prescriptions are, what common dosages are for a given medication. And so then if the doctor puts in their prescription level, it'll just ask, did you mean to prescribe 10 times the normal dose? And it can actually it can actually prevent a lot of problems that way and make sure that a lot of people are more healthy. Another good, there have also been a lot of good examples. Recently, I think Google got some press for doing something to help with breast cancer detection. It's also very helpful in detecting things in radiology images. There's also been some work in helping doctors prescribe medications more effectively. Something that my advisor worked with a few years ago is she had a whole bunch of data from autistic patients, and some of them, and some data with some co-occurring disorders. And there are sort of two different disorders that usually co-occur with autism. But doctors hadn't really noticed this because many things co-occur together. And just by doing some clustering, she was able to see that there are sort of these two phenotypes of autism, one that usually co-occurs with disorder A and one that co-occurs with disorder B. But in general, I would urge you to go to Google Scholar or follow some of the names of people I mentioned during the talk, and you'll see a lot of cool advancements there. I meant with lab results in context of diabetes, so using them to know what a person has diabetes in regards to the insurance case, such as glucose level. Yes, that would be another thing that you could look at. You could look at their lab results. Often it's difficult to diagnose based on just one lab result. So it makes sense to look at other tests, but yes, that is a perfectly reasonable thing to look at if you're trying to diagnose someone for diabetes. Jessica, what type of expertise or effort is most needed to help advance the projects you mentioned? I think it depends a lot on the project. For a lot of these projects, you actually you don't need to know the most state-of-the-art machine learning. Like the project that I was talking about in separating two phenotypes of autism was just some sort of basic clustering methods that you would get in probably any introductory machine learning course. The really notable thing was just having information, was just having the medical data and understanding and having a good collaborator to help understand what was going on in the data. So like I said, I think you don't need to know necessarily the most detailed machine learning, but knowing some machine learning and working with this type of data, you can actually have a pretty substantial impact. So great question, Jessica. I think that is everything. So have a good day.